Okay, let us continue. So before the break, we looked at how to solve the least squares problem to compute the optimal parameter that we star, which was x transpose x inverse x transpose y, and then we also talked about the metric, right? So now let's do another example problem. Okay. So this time I'm going to do a synthetic example. Okay. So unlike the housing price prediction problem, like which was a real application, in this case, this is a synthetic example where what I did is I took a sine wave, okay, so the function that I'm looking for is the sine wave, but then I'm going to add a bit of noise to the sine wave, okay? So my y is going to be sine of 2 pi of x plus some epsilon noise. The epsilon is a Gaussian noise with zero mean and let's say 0.3 standard deviation, okay? So the exact details doesn't matter. Like, so what matters is I took a sine wave, sine 2 pi x, and added some Gaussian noise to it, okay? So given this particular x, the output of the sine function is going to be this, but because I added some noise, instead the output is this, okay? As you can see, there is a little bit of noise everywhere. So these are the data points. Okay. Is that clear? Okay. So given these data points, I'm interested in coming up with a model that will make good predictions for the unseen x. Is that clear? Now, I think with this synthetic example, we have this advantage that we know the true function, right? With a lot of practical applications, we don't know the true function. Like, let's go back to the housing price model. We don't know how the true function for this function is going to be like, right? So nature somehow has a process which gives the output, and we don't have access to this process, right? But in this case, because I created this example, I know that the best possible function that I could find is basically sine function. Is that clear? Okay, so this is my problem. I want to come up with a regression model which given x is going to predict y. So what would happen if I just use my linear regression model? Yeah, it's not going to fit well. Yes. So what can we do with the linear regression model, right? Like, so we can just draw lines, right? So if I just fit the linear model that we developed before the break, this is exactly how that model is going to look like. Okay, not too bad. It's not a sine function, yes, but it is not too bad in the sense it is actually capturing the main axis of variation for this particular set of examples, right? However, clearly this is not the best model that one could think of, right? Like, which kind of means that we need to start developing even more complex models than the linear model that we have seen so far. Okay, so we're going to develop another class of regression models. Okay, so these are called polynomial regression models. Okay, so with polynomial regression, the model is going to look something like this. So it's going to be y hat of x given w is equal to W0 plus W1x. This was my linear model, right? So the linear model had degree up to 1. I'm just going to add higher order degrees, like so, plus W2x square. Let's say we add up to m, degree m, Wm x power m. Okay. Now, basic algebra, like so you would have plotted these functions, right? Like so, when you plot just W0 plus W1x, you're going to get a line, right? So when you plot W0 plus W1x plus W2x square, what kind of functions you will get? You'll get a quadratic function, right? Like so it's going to look something like this, right? So what about, well, maybe I'll add just one more term, okay? So up to W3x power 3. So what kind of functions you'll get? Now, like this. But how is it different from what I have? No? Say. Okay. So given a function, the trick to know the degree of the polynomial is just to see how many like turning points are there in the function. Okay. So in this case, you have one turning point, right? So this is actually degree 2. Okay. So here you have 2 turning points. So it's degree 3. So the number of turning points in the function is roughly like 1 times less the like minus 1 of the degree. Okay. So this just means this all I mean to say here is the more degree I'm going to add, the more complex my function is going to look like. Like if I have, for example, if I have a 10-degree polynomial, okay, the 10-degree polynomial could look, well, something like this. Like so, all to say that you can have many variations in the function, like the more complex the polynomial is. Is that clear? Okay, so now let's go back to the equation once again. So y hat of x given w is given by w0 plus w1x plus w2x square all the way up to wm x power m, right? Again, we are going to convert this into like a vector notation. But before we do that, is it a linear model or a nonlinear model? Yeah, so how many of you think this is nonlinear model? Okay, just one. So why do you think this is nonlinear? So x squared. So as I said before, you define a linear model based on linearity with respect to the parameters. Okay. With respect to parameters, this is still a linear model. Okay. So why do I put emphasis on the parameters? We're going to see. Once we start solving this model, you will see that I don't need to do anything for this model specifically. Like I can just use the same solution from the linear model that we developed before. It will just work out of the box. Okay, so we will see how that happens. So first, let's convert this into a vector notation. So I'm going to put a 1 here. So W0 times 1. Well, or I can just put x power 0, right? X power 0 is 1 plus W1 times x power 1 plus W2 times x square all the way to Wm x power m, right? So this I can write as summation j is equal to 0 to m, okay, wj x power j. And if I want to write this in vector form, I'm going to have my w vector, which is w0, w1 all the way to wm, and my x vector, which is x power 0, x power 1 all the way to xm, and my model y hat of x given w is simply w transpose x. Okay. Yeah. It's a different feature. Okay, so the observation here is just a single X, right? The input feature, okay, so the input to the system is just a single X, but then you're creating multiple features out of it. You're doing X power 0, X power 1, up to X power M. So these are just features. Okay, so the moment you start thinking about these in terms of features, right? Now, the fact that it is X squared doesn't matter. It need not be X squared. It could be, for example, I don't know, pi times X could be one of the features, or sine of X could be one of the features, right? You could have whatever features that you want here. Okay, so for polynomial regression, our features are X squared, X cubed, X power 4, etc. But you could construct any kind of feature that you want and put it here. Okay, so the moment you start seeing this as feature, then this model is exactly the linear model that we developed before, right? So this is same as linear model. The only difference is the previous example, we had one feature. Here we have M features, right? So the solution for this model is still the same, W times, like X transpose X inverse X transpose Y, right? So we don't need to solve this separately. Like we have the solution already. So we could just take the X, construct the polynomial features, and like use the same linear regression solution. Yeah.
But I choose that is more important.
Okay, that's a good question. The question is, does higher degree feature means that the feature is more important? Not necessarily. Okay, so what feature is more important? Well, I think that's a more deeper question. So we'll get to that later. Okay, so for now, we are just constructing these features and trying to solve linear regression problem. Okay, so now you can just decide what number of feature you want, like what degree you want, and then solve the linear regression problem with that degree. You're going to get different functions, right? So here I'm plotting that for a bunch of degree values. Okay, so first let's start with degree is equal to 2, this example, right? So when degree is equal to 2, you get W0 plus W1 X. Yeah.
Can features be on the same axis?
What do you mean?
Okay. In some way, we have different reviews to place them on different axes.
Not necessarily. Like, so the reason why we are having different degrees here is basically we are looking for a more complex function, right? Okay, well, we can talk about it.
Yeah.
Okay, so for different degrees, right? Like, so degree 2, degree 3 polynomial, degree 4 polynomial, degree 5 polynomial. So the orange color is the function that you would get by solving least squares. Is that clear? So as you can see here, with more degrees, you're getting something that is closer to sine, right? So now what will happen if I just keep increasing this degree? So here we have degree 6, 7, 8, and 9. Okay. So what is happening here? Yeah. Yes, when you are at degree 9, right, you have 10 examples here. So with degree 9, the number of parameters you have is 10. So it is somehow exactly fitting the example that you have, right? Like, so this, what would be the training error for this polynomial? 0. But is it a good polynomial? Is it a good function? Is it a good approximation of sine function? Yeah, so this is kind of overfitting to just the training example, okay? So this is trying to fit the training example so much at the cost of losing generalization power. Like, so this is not going to be a good model for generalization, right? Because the curve looks so bad that like you get a new X, you're going to get a very high error. Is that clear? So this is what we're going to call as overfitting. Okay. So what is overfitting? So overfitting is when your model is so complex that it has almost zero training error, but the test error is going to be very high. So sometimes it's not a good idea to just fit the training error too much, okay? Again, I think we will talk about this again and again throughout this course. The goal of machine learning is not to get zero training error. It's not to get zero training error at all, okay? So the ambitious goal of machine learning is to get zero generalization error. Okay, so, well, we will see in a later class that it's almost impossible. You can never get zero generalization error, okay? But we will strive to get zero generalization error. We'll try to get as least generalization error as possible, okay? So that is the goal. Getting zero training error is not the goal, okay? However, there is a mismatch in the process, right? Like the process is using the training set. We're trying to minimize the error function with respect to the training set, while ideally we should be minimizing the error with respect to the whole distribution, but then we don't have access to the whole distribution, right? Like so there is a bit of mismatch here. So we're going to talk about the deep implications of this mismatch probably in like 2 or 3 weeks. Yeah.
And is there a way to find the best degrees when we're doing CDC?
Yeah, I will talk about it. So the question is like, how can we find the best degree then? Right? So again, because this is a 1D example, I can plot different degrees, and visually we can say, oh, this looks nice, this doesn't look nice, right? But we cannot do this with 100 features. We cannot do this with a million features. So when your data is more than 2 or 3 features, you cannot visualize the data, right? So then how can I quantitatively detect that this is a good degree, this is not a good degree? Any thoughts? Someone else? So there are 1 or 2 usual answers. Like, yeah?
The things that we parameters.
Okay. Okay. So you will have a separate test set, which is not part of the training set, right? Like we talked about it last week, right? And you're going to compute the performance in this test set. So if the training set performance is so good, but the test set performance is so bad, then you're overfitting. Is that clear? Okay. So here, so what I have done is for different degrees of polynomial, I'm plotting both the train RMSE and test RMSE. Okay. So you see here that the train RMSE, it strictly gets better and better with larger polynomial, which makes sense, right? So the larger the polynomial, the more powerful the function is, right? So it should be able to fit the function, fit the data better. Okay. So you see that when you reach 9 degree, the training error is 0. So 10, 11, 12, like if you extend this, like the training error is just going to be 0. Like after 9 degrees, because you have only 10 examples, like this polynomial can just fit the training data perfectly. Okay. But then the problem really happens with this region, right? Like, so it looks like the test error is going down up to some extent. So then it is increasing, right? So we're going to call this region where the training error is going down, but the test error is going up, right? So we're going to call this a bad region. Okay. And this is roughly the good region. So based on this curve, like what do you think is the best degree for this particular example problem? 3? Yeah, that's 3. So the 3-degree polynomial has the least test error. Is that clear? Any question?
The simulate the read shows like what I don't know different at the graph.
So the 0 degree, yeah.
Yeah. Why does it show not the different?
So what do you mean by no difference? It has some error, right? Like it has some training error tested. Like you should not read too much into this one. So by 0 degree, I mean like you just have the bias, right? So it's just like just a bias, which means it's a constant prediction. It's going to always predict the average. So this is just the bias. Okay. Okay. So here's a deeper question to think about. Just 1 second. It looks like degree 3 is better in this case, right? However, a 9-degree polynomial actually contains the 3-degree polynomial inside, right? So shouldn't I be able to find the 3-degree solution even when I'm using the 9-degree polynomial? So all you have to do is just set the rest of the degrees to 0, right? Like so you can just set W4, W5, W6, W7 all 0. Then you get the 3-degree. You can recover the 3-degree polynomial from the 9-degree polynomial, right? So why is that not happening? Like why is it that when I use a 9-degree polynomial, I'm not finding the better solution? Because there's clearly a better solution. Like so whatever solution you find here, this is not the best solution for 9-degree. The best solution for 9-degree is actually setting 4 to 9 degrees to 0 and just using the first 3 degrees. That's going to give me much lower test error, right? Like so why is that not happening? Question or comment?
I really need something
We need some external pressure to do that. But why do we need an external pressure? Like this should happen naturally, no? Not necessarily.
Because the objective function does not see like the test samples, so.
So the objective function, well, yes, okay, by the way, the problem is way more deeper, okay? But you're right, like, so the objective, because the objective function doesn't see the test examples, like it is just looking at the training example, right? Like, so it is not really minimizing the test error. It is minimizing the training error, right? So to minimize the training error, this is the most logical thing to do. Setting the remaining to 0 is not the logical thing to do, right? Like because we care about minimizing the training error while we are doing the optimization, right? Because we have access to only the training set, which is why you need external pressure, okay? Because the actual process is not sufficient. The actual process is just looking at the training set, and just looking at the training set is actually a bad idea for generalization. Question or comment? Okay, so now we can actually verify this. We can actually verify that this is happening because there's only training set and the model is just trying to fit the training set, okay? So how do we do this? Like, so here, I'm writing the solution for the linear regression problem, like the polynomial regression problem, for different degrees, the polynomial, okay? So when m is equal to 0, there's only one parameter, the rest is 0, right? When m is equal to 1, it's w0 plus w1. When m is equal to 3, w0 plus w1 x, wk square, w2, and so on, right? As you can see here, as the degree grows, the parameters are getting bigger and bigger, right? So this is happening because the model really wants to get 0 training error. So one way to get 0 training error when you have 10 parameters and 10 weights or parameter, like 10 parameters and 10 examples, is to increase the number as much as possible, like so that you are for sure getting the exact numbers. Okay, so there is some sort of overfitting happening here with respect to the weights. Is that clear? Yeah. When the features are dependent on one another, you get massive values. I have to think about it. But I don't think that is the reason this problem is happening. Okay, but that part I need to verify. Okay, so any questions? Okay, now that we know what is happening internally, can you think of ways to fix this problem? Someone else? Fresh hands? Let's see. Anyone else? Like, so, like, how can we fix this issue? Like, so, like, now we know the problem, right? Like, so when I have m is equal to 9, the weights are just growing too much, which leads to the overfitting, the training set. So, how can I fix this issue? Yeah.
More training sets.
Okay, so that's a good solution. So, okay, we're going to look at a bunch of solutions. Okay. So the question we are interested in is how to solve overfit. I'm not okay with the 9-degree polynomial overfitting. Okay, so we're going to find ways to fix this overfitting issue. So the first solution that was proposed is to basically add more data. So can someone tell me, can someone else tell me why adding more data would someone, I'll come back to you, but like, can someone else tell me why adding more data would help with the overfitting problem? You know, I'm going to randomly pick people. Okay, so yeah. Yes, the more data points you have, a 9-degree polynomial cannot fit everything, right? Like, so now it will start making sacrifices. Like, so it's not going to be able to, let's say, instead of 10 examples, let's say I have 100 examples. Okay, so this is how it's going to look like. So here you see the same 9-degree polynomial. I think here we have roughly 20 examples. Okay, I guess this is 20, but here I have 100 examples. The more examples I add, the model cannot overfit, right? Like, because it doesn't have the capacity to overfit. So now the best way to reduce the training error is to look for regularities. I'm going to look at, oh, how does a trend look like? I'm just going to follow the trend as much as possible, and like that looks closer to sign function. Is that clear? So typically when your model is overfitting, it is always a good idea to just add more examples. So then you're reducing capacity of the model. Like, the more examples you add, at some point the model is not going to have enough capacity, so it's going to stop overfitting. You had some question? No, you? Yeah.
What I learned, it might be worse was training of like different data.
What do you mean by that?
Okay, different.
Okay, so is the first solution clear? So what else can we do? So what else can I do? Yeah. No, well, now you're jumping too much. So some other solutions. Let's not talk about that now. Yeah. 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 So you somehow want to avoid the parameters becoming bigger, right? But even before that, there's actually, well, there's another simple solution. Solution 2. So let's say you cannot get more data. Like, I give you 100 data, like 10 data points. I'm telling you that these are all the data that you got. You cannot increase the data points. You cannot increase the data point, and you see that 9 degrees over. So what is the most logical thing you could do? Okay. Yeah, that's the same solution as he said, like, but before that, right? Like, so even simpler solution. if you know that 9 degrees overfitting, yeah? You already have just 10 examples. You don't want to drop this. Yeah.
Find the better two.
Okay, okay. Any other thoughts? Yeah.
Can you do this process to make it all training sets and then generalize from all those?
But you have just 10 examples, right? So you have 10 examples. I'm not giving you more examples. And you see that 9 degrees overfitting. Yeah. Changing the error function. Do you think changing the error function would help? Okay, okay. So then you're all arriving at similar solution. But before I jump to that solution, like I want to propose another simpler idea, which is basically just to reduce the degree. You have limited amount of data and you see 9 degrees overfitting, right? Try reducing the degree and see if overfitting goes away. That is a valid thing to do too. Okay. But then the problem with this approach is, well, you need to try many things, right? So it becomes a trial and error. It's not exactly trial and error. Like you can do it in a smarter way. Okay. But the third solution, which is what I think a lot of you proposed, is to somehow penalize the weights from growing too much. Okay. So how do we do that? So the most standard way to do this is called L2 regularization. Okay. So L2 regularization is going to change the error function. So the usual error function that we had, which is E of W is equal to 1 over 2 summation I is equal to 1 to capital N y hat of x n given W minus they always confuse I and N. So the whole square. This was my error function, right? Okay. So now I'm going to add an extra term to this error function, okay, which is plus lambda by 2 times the L2 norm of W. Okay, let's call this a modified error function. Okay, where the L2 norm of W square is basically W transpose W. So basically W0 square is W1 square all the way to WM square. So here I'm not just minimizing the error, I'm also trying to minimize the L2 norm of the W vector, which means I'm looking for low norm vector. I'm looking for W vector which is as small as possible. This is an extra condition, or as someone said, this is the extra pressure that I'm putting on the problem. Okay, so I'm adding a constraint here. I'm saying, oh, I don't want you to just minimize the training error because it is not very useful to just minimize the training error, right? Like I also want you to come up with solutions which has smaller W, because we know that having bigger W is a problem. Is that clear? Yeah. Okay, that's a good question. So here, how does this help, right? How does this term really help? So these are two functions, two objectives that we're trying to minimize, right? There is a trade-off between the two objectives, which is determined by this lambda. So the lambda is a regularization coefficient. Okay, so the lambda that you see here is regularization coefficient. Okay, so if you put a very high lambda, then you're telling the system that, oh, I want you to focus a lot on this over this. Okay, so you'll try different values of lambda, like it's going to give different strength to the regularization, right? So you cannot get W close to 0. Like if it is too close to 0, then this error is going to increase, right? So there is a trade-off. Like so, like if you have a minimum for this joint error function, that is going to be hopefully the best of both, like something that has as minimum training error as possible, at the same time also as small weight as possible that helps with the minimum training error. Is that clear? Okay, so now let's try to solve this error function. So the error function is given by 1 over 2 y minus xw transpose y minus xw plus lambda by 2 w transpose. I'm directly writing it in vector array. So this is my error function. I'm going to differentiate this, set it to 0, and I will get my w. Okay. So what we are going to do is basically dou E by dou W is equal to 0. Okay. So let's differentiate. The first term is going to be minus, I'm directly writing the first term's answer. So it's going to be minus x transpose y minus xw, right? So this part we did it before the break, right? Plus, when I differentiate lambda by 2 w transpose w, I'm going to get lambda by 2 w square differentiation is 2 times w is equal to 0. So this cancels. So minus x transpose y minus x transpose xw plus lambda w is equal to 0. Right? So x transpose xw plus lambda w is equal to x transpose y. Is that a mistake?
Plus, plus, it's transport.
Oh, okay, sorry. Okay. So now x transpose x plus lambda times w is equal to x transpose y. So w is given by x transpose x plus lambda I inverse x transpose y, where I is the identity matrix. Okay. So this is the solution. Now the solution for least squares with L2 regularization looks exactly like the least square solution, which was x transpose of x transpose y. All I'm doing is I'm adding some small positive value lambda to the diagonal of the x transpose x matrix. Is that clear? So this you can implement, right? I think you will implement the regularization solution in your assignment. Okay, so now I can use this W. And in this case, I have to decide what is the lambda that I'm going to use for, right? So depending on the value of lambda, I'm going to get different solutions. Okay, so let's look at the example here. So here, I'm using degree 9 polynomial, but I'm trying to use different values of lambda. So in the first example, the ln of lambda is minus 10. I'm using it in the ln space so that it's easier to change. So ln of lambda is minus 10. Here, ln of lambda is 3. Okay, so you see that as I increase the value of the lambda, the model gets closer and closer to linear model. So why is this happening? This is happening because you go back to this equation, right? As I keep increasing the value of lambda, I'm giving too much weight to having a model that has W that is close to 0, right? As small weight as possible. Now that is going to collapse the model to a linear model. So in extreme case, like when I have very high value of lambda, I will recover the linear model. When I have lambda is equal to 0, then I'm going to get into the 9-degree polynomial, which is perfect. Okay. So ideally, I want my lambda to be between these two extremes, like something that is in between. That's a sweet spot, which gives me something that looks like a sine function. Is that clear? So here you see, when ln lambda is minus infinity, which means lambda is 0. So when lambda is 0, you see overfitting happening. When lambda is very high, you see the model getting close to the linear model because everything is getting close to 0. With the lambda that is in between, you get a model that is looking like a 3-degree model, right? Like so now with this extra regularization, I was able to recover the 3-degree model by using a 9-degree model. Is that clear? Yeah. Oh no, the bigger model, bigger lambda just makes all the parameters close to 0, not just the earlier model, earlier parameters. The bigger the lambda, everything goes close to 0. Then the model looks like a line. Okay, so if I have to summarize this discussion, right, like, so when lambda is too small, right, then there is no regularization happening. Okay, if lambda is too high, okay, so then actually it's going to create too much regularization. So we need to pick the right lambda, right? So this lambda, we're going to call this the hyperparameter of the model. Okay, so why am I calling this hyperparameter? It's not a parameter. So W is the parameter of the model. I'm calling this a hyperparameter because I'm not going to learn the lambda from data. The parameters, we usually learn it from the data, right? This hyperparameter is something that I'm just going to pick by myself before I start learning. So I need to decide what lambda to use. And once I fix the lambda, then you can solve the regularized least squares plus delta regularization problem. Okay, yeah?
It's still how to pitch the right degree.
Sorry?
It doesn't tell us how to pitch the right degree.
Yeah. No, that's a good point. So this is still not telling you how to pick the right degree, right? Like, so the benefit, okay. To be fair, if we go back to the polynomial regression, the degree of the polynomial is also a hyperparameter, right? So the degree of the polynomial is a hyperparameter because you need to decide what degree to use. So then you have your solution, right? So we don't know how to pick the degree, which is why we followed this regularization approach. The benefit of the regularization approach is you can just pick whatever high value degree polynomial that you want. Then you tune the lambda. We're just converting the problem from one space to another. We are not solving the problem yet. Okay, so we are just, instead of picking different degrees, I'm going to pick a very high degree and tune the lambda. The tuning of lambda is nice because I can just tune it to very high or to very low, and that is going to give me some complexity for the model. Is that clear? Yeah. Oh yeah. Well, okay, that's always confusing. So I'm putting ln lambda instead of lambda just because the scale is nicer. You don't need to do this. You can just consider this to be lambda is equal to 0 and lambda is equal to like whatever the ln inverse of -1. Like it's going to be very small to very large. Okay. Okay. Now the most important question is how to choose lambda. Any idea? How to choose lambda? Checking manually, like trying different lambda. Okay, let me explain the process that he's proposing. Like, so I'm going to take, sorry. So this is my lambda value. And this is my RMSE. Okay. So when lambda is 0, you will overfit, right? So if I plot the training error is going to look something like this. The training RMSE is going to be 0 when lambda is 0 because you are overfitting, and it is just going to keep increasing with more regularization. So this is clear? Now, how would the test RMSE look like? So the test RMSE is going to look something like this. Okay. So it's going to be very high when you're overfitting, and there's a sweet spot, right? So this is the best possible lambda that you could use. Is that clear? However, there is a deeper problem with this approach. This is test RMSE. See, the black is train RMSE, the blue is test RMSE. Okay. So there is a deeper problem with picking lambda this way. What's the problem? Yeah.
Well, we cannot test anymore.
Yes.
We
We cannot use. Okay, what was the purpose of the test set? The purpose of the test set was actually to test the model. Like it was a proxy for real life generalization, right? So I'm actually picking the best lambda based on the test set. So which means the test set is not a test set anymore, right? So it is a bad idea to pick lambda based on the test error. But can I pick the lambda based on the training error? Like what would be the best lambda if I pick it based on the training error? 0, right? So it is useless to pick the lambda based on training error because we know that the best training error is always when lambda is 0. So I cannot use the training error to pick the lambda. I also cannot use the test error to pick the lambda. So what can I do? We can split the data again, right? Now we need a separate data set just to tune our hyperparameters, okay? So what I'm going to do, like last week, I told you that when somebody gives you the data, you split it into train and test, right? This doesn't work anymore if you have hyperparameters to tune, okay? So what we are going to do is we're going to further split the data. So we're going to split the data into 3 parts. We're going to call them the training part, okay, and validation part and test part. Okay, I'm going to use the training part to train the model. By that I mean minimizing the error function with respect to W, right? So that's what I'm going to do with the training part. And I'm going to use the validation part just to pick the best lambda. Okay. Once I pick the best lambda, finally I'm going to evaluate the model's performance with the test. Is that clear? Any question? So if I have to summarize this process, right, this is what we are going to do. So for different values of lambda, okay, I'm going to train the model and I'm going to compute the validation error. Okay, so that is my first step. So then I'm going to pick the best lambda that has least validation error. And finally, I'm going to compute the test error for the model with the chosen lambda. Okay, so this idea of picking your hyperparameter for the model based on validation set, right? Like, so this whole process is called model selection. We are selecting our model, like so. Like now, the model comes with different hyperparameters. So I'm going to select the model by picking one lambda, and this picking happens through the validation set. Is that clear? So now I'm going to go back to the same problem. So here I'm plotting not the test RMSE, but the validation RMSE. This one. So I'm plotting the training RMSE and the validation RMSE. Okay, so you see that the training RMSE is 0, and it keeps increasing regularization, right? And the validation RMSE, there is a sweet spot. So I think the best thing is approximately here. This is the good region for lambda. Is that clear? Question? No, well, like so, it's not like that. Like in the first step, you're trying different values of lambda and you're computing both the train and validation error. So for training the model, you'll use a train set. To compute the validation error, you're using the validation. Okay, yeah.
I don't think the graph. No, the difference is small. With the same that,
This one?
yeah, that's,
Okay.
I don't understand it.
So do you understand the training curve? The training has to be zero when no regularization happens because you're overfitting, right? And it will just keep increasing, right? On the other hand, the validation or the test is going to be very high when you're overfitting. It's going to decrease up to some point. Then it is again. But this is just a theoretical curve, okay? It doesn't always look like a U curve. Like, so for example, in this example, it doesn't look like a U curve, right? It's approximately U. By U, I mean there is some high value on the left side, some high value on the right side, and there is sweet spot in between. Is that clear? Any questions so far? Okay, let's take a 10-minute break.